These are examples from Lesson 3.5, Properties of Triangles. In this video, you will learn to prove and use two new theorems involving properties of triangles, the Triangle Angle Sum Theorem and the Triangle Exterior Angle Theorem, or what's called also the Remote Interior Angles Theorem. Example 1. Prove the Triangle Angle Sum Theorem. In this example, you will apply any of the angle pair postulates you have learned along with the new triangle theorems you have just been introduced to. Remember, when we prove a two-column proof, we have the given statement and the prove statement, and this is our goal, is to write the prove in our last statement here. Our first statement needs to be given. We have a triangle here, XYZ. We're trying to prove the Triangle Angle Sum Theorem, which basically states that if you have a triangle, then all the interior angle sums, or sum, is 180 degrees. So, given triangle XYZ, we want to prove that the measure of angle X, this interior angle, plus the measure of angle 2, this interior angle, plus the measure of angle Y, this interior angle of this triangle, is 180 degrees, or 180. So starting off with the given, triangle XYZ is given to us. Then next statement, angle 1 and angle XZB are supplementary. Here's angle 1 and angle XZB, that's this one right here, are supplementary. We know that because they create angle AZB, straight angle, or a line. And we just kind of ignore this segment right here. Angle 1 and angle XZB. That's by the definition of supplementary angles. Once we've established that, now we can say that the measure of angle 1 plus the measure of angle XZB is 180 degrees. Because they form a line and the two angles are adjacent by this side right here, they're a linear pair, and now we can say by the linear pair postulate that their sum is 180. Now that we've established that, we take the measure of angle XZB, and notice that it's made up of two angles, angles 2 and 3. So if we show that these two can be added together, that will give us the angle XZB, angles 2 plus 3. That's the angle addition postulate. Then we have the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 is equal to 180. That comes directly from the definition of supplementary angles. Remember, you can have more than two angles added together to give you 180 degrees, and that's still the definition of supplementary angles. From this point, we state that angle 1 is congruent to angle X. So over here we've got one arc on 1 and one arc on angle X. We also notice that angle 3 and angle Y are congruent. Angle 3 and angle Y. What do angles X and 1 have in common, and what do angles Y and angle 3 have in common? Angles 1 and angle X are both alternate interior angles. Angle X and angle 1 are alternate interior, and because these are parallel, a parallel segment and a parallel line, these must be congruent by the alternate interior angles theorem. And this is also true for the other statement, angle 3 and angle Y. Angle 3 and angle Y are alternate interior angles cut by transversal ZY Alternate interior angles are congruent because these are parallel. There's the transversal. After we've established this, we now see that the measure of angle 1 and the measure of angle x are equal, because if two angles are congruent, their measures are equal. And the measure of angle 3 and the measure of angle y are equal, because if two angles are congruent, their measures are equal also. So both of these are by the definition of congruent angles. When we get to this stage of the proof, we notice that if we use statement 7 and use these, the measure of angle 1 equals the measure of angle x, and the measure of angle 3 equals the measure of angle y, and we go back to statement 5 and replace the measure of angle 1 with this one and the measure of angle 3 with this one, and rewrite it here, that would be the measure of angle x plus the measure of angle 2 plus, instead of the measure of angle 3, the measure of angle y, equals 180 degrees, or 180. We use these two statements to use substitution. Substitution property of equality, and we used statements 5 and 7. Let's check it out and see if it works. The measure of angle x plus the measure of angle 2 plus the measure of angle y is 180 degrees. Notice we used an auxiliary line, line AB, parallel to one of the sides of the triangles to prove the Triangle Angle Sum Theorem. Next, example 2. In this example, you will apply any of the angle pair postulates you've learned along with any new triangle theorems you've just been introduced to. Now, there's different ways sometimes to solve when there's multiple variables in a geometric diagram. It doesn't necessarily mean you have to do it in a certain order. We're sometimes forced into finding a particular variable value first before finding the other variables. This doesn't happen to be one of those. Well, actually it does. We have to find x first, but then whether we find y or z second doesn't really matter. In addition to that, there are different ways we can go about doing it, and sometimes you can use different postulates or theorems. So the way I'm about to show you is just one of several ways you could do it. What are the values of x, y, and z at the right? We've got triangle ABC, and we have triangle ABD. We also have triangle BDC. These two triangles make up the largest triangle ABC. Notice we've got three of the angles. We've got x, y, and z here. X needs to be found first. Well, I'm going to choose to find it first. I just noticed that y can be found right away, but I'm going to choose to get x first. I'm going to cover up this triangle BDC. Notice triangle ABD. We've got two of the three interior angles already. So by the Triangle Angle Sum Theorem, we can make the statement the measure of angle A, or 59 degrees, plus the measure of angle ABD, or 43 degrees, plus the measure of angle ADB, or x degrees, has to equal 180 degrees by that theorem. And we solve the resulting equation. When we solve, we get x plus 102 equals 180. After adding those two, then subtracting 102 from both sides, we get x equals 78 degrees. We found the value of x, which is an angle measure, in 78 degrees. Next, I'm going to choose to find z. I could find y, but I'm going to find z. Z right here, notice that this is now 78 degrees. If I cover up line segment AB and AD, or AB, notice that we have a setup for the Triangle Exterior Angle Theorem or the Remote Interior Angle Theorem. Those are the same thing. We have this outside angle, triangle BCD. Exterior to it is angle X here, so 78 degrees. And according to the theorem, the exterior angle is equal to the sum of the two remote interior angles, which would be 49 degrees and Z degrees. These are the two angles furthest away from this one. So by the Triangle Exterior Angle Theorem, or it's also called the Remote Interior Angles Theorem, we can now say 78 degrees is equal to the sum of the two remote interior angles, 49 degrees plus Z degrees. Now we can solve for Z by subtracting 49 on both sides, and we get 29 degrees is equal to Z degrees. So Z is 29 degrees. Finally, Y, there's two ways we can find Y. We can use the linear pair postulate with X and Y, or we can use the Triangle Angle Sum Theorem with triangle BDC. I'm going to use the Triangle Angle Sum Theorem with this one. So by the Triangle Angle Sum Theorem, we have the measure of angle BDC, which is 49 degrees, plus the measure of angle C, which is Z degrees, which is now 29 degrees, plus the measure of angle BDC, which is Y degrees, equals 180 degrees for the entire sum of the angles in the triangle. Then solving this equation, we combine like terms, which we add these two together. We get Y plus 78 equals 180. Then subtracting 78 on both sides, we get Y equals 102 degrees. So Y is 102. We've got X, Y, and Z. Example 3. These two parts of the problem focus on setting up the equation that is referred to in the Remote Interior Angles Theorem, or what is also called the Triangle Exterior Angle Theorem. So that's what we're going to focus in also. The math is pretty simple. So taking a look at this first one here, A, what is the measure of angle TUW? And T is here, U is here, V is here, and W is over here. And so angle TUW is this one right here. This angle is exterior to this triangle, and the two remote interior angles to that exterior angle are angle V and angle W, not angle WUV. This one right here is adjacent to it, so it's the non-adjacent two angles. So by the Remote Interior Angles Theorem, or what else is known as the Triangle Exterior Angle Theorem, we can say the measure of angle TUV, that's what we're looking for, equals the measure of angle V, this one right here, plus the measure of angle W, this one right here. Substituting in the values that we know, we have the measure of angle TUV equals 80 degrees plus 18 degrees. And then it's as simple as adding those two or solving the equation. The measure of angle TUV equals 80 plus 18, which is 98 degrees. In part B, we use the same theorem, except it's just done slightly different algebraically. We've got this triangle here. This is point F. This is point G. This is point E. And this up here is point D. So what is the measure of angle E, or 2? I'm going to write, we're going to use the remote interior angle theorem, or the triangle exterior angle theorem. So by the triangle exterior angle theorem, or what else is known as the remote interior angles theorem, set up an equation first. We have the exterior angle, which is the measure of angle FGD, that's this one right here, equals the sum of the measures of the two other remote interior angles, the measure of angle D plus the measure of angle E. So substituting in all the values that we have for those, we have 124 degrees equals the measure of angle D, 59 degrees, plus the measure of angle E is actually the measure of angle 2. Subtracting 59 from both sides, the measure of angle 2 is going to give us 65 degrees. Two ways to use the triangle exterior angle theorem, or what is also known as the remote interior angles theorem. Now for an application problem. Example 4. We can apply the triangle exterior angle or the remote interior angles theorem to real world situations, just as we can apply the triangle angle sum theorem to real world situations also. When radar tracks an object, the reflection of signals off the ground can result in what's called clutter. Clutter causes the receiver to confuse the real object with its reflection. This is called a ghost. Below there is a radar receiver at A, point A, which is right here, an airplane at point B. Here's point B. Here's the airplane up in the air. And the airplane's ghost, or reflection, at point D down here. And they drew a reflection of that airplane. You can kind of see it. This would be the line of reflection, the horizon line across there. And so this is D. What is the value of X? Right here we have a triangle from the airplane down to that point C, and then this is 30 degrees. Then we have 80 degrees, the angle between the line segment that goes down to point C from the airplane over to its reflection. That's 80 degrees. And we want to know what X is, the angle from the plane, this line of sight to the plane, down to the reflection of the plane. So we've got this situation where we have a triangle and an exterior angle to that triangle. So by the triangle exterior angle theorem, or the remote interior angles theorem, the measure of angle BCD, that would be this exterior angle here, equals the measure of angle A, which is at the air traffic controller tower there, plus the measure of angle B, the angle at which the vertex is the plane in the air. Substituting the values we know, we have the measure of angle BCD is 80 degrees, equals the measure of angle A, which is X degrees, plus the measure of angle B, which is 30. And so the math is pretty simple here. Subtract 30 from both sides, and X equals 50 degrees. There's a 50-degree angle from the line of sight to the plane, from the air traffic controller down to its reflection. And finally, example 5, find the value of X, then find the measure of angle KLP. KLP, that's this one right here. Okay, once again, algebra is an integral part of geometry, and so when you take a look at this, we've got this line and this triangle coming off from the line with two other sides, and we do have an exterior angle to that triangle, so let's try using the remote interior angle theorem. So by the remote interior angles theorem, which is also called what? Triangle, exterior, the triangle exterior Angle Theorem, those are the same. We can say the measure of angle KLP is equal to the measure of angle P, these are the two remote interior angles to it, plus the measure of angle LMP. We need all three letters because there's more than one angle here. So the measure of angle KLP is given to us as 5x plus 38 degrees equals the measure of angle P, which is 4x minus 13 degrees, plus the measure of angle LMP, which they give us is 2x plus 36 degrees. Now we have an equation to solve. Drop the parentheses, combine like terms on the right side. We get 5x plus 38 equals 4x plus 2x is 6x minus 13, and then plus 36 is plus, 23. And then both sides have an x term, so we get rid of one of the x terms. I'm going to subtract 5x from both sides. We get 38 on the left and 1x or x plus 23 on the right. We kind of lucked out. We didn't get anything but a 1 here. So now we only have one more step to go. We subtract 23 from both sides, and x is 15. So there's our first answer. We found the value of x. Then, to find the measure of angle KLP, we use what we were given, 5x plus 38 degrees. 5x plus 38 degrees. Substituting in what we found for x, 15, we have 5 times 15 plus 38 degrees, which gives us 75 after multiplying these two together, plus 38 degrees. And then that gives us 113 degrees for the measure of angle KLP.